All right, everyone. So we're covering chapter 24 here, which is on electromagnetic waves. So we're going to talk about some of the properties of electromagnetic waves, who discovered, very important, let's say, a relationship of electromagnetic waves to light. And we're going to see that electromagnetic wave is basically a wave that combines electric and magnetic fields, okay? And it can propagate through vacuum, okay? And remember, this is one of the differences between mechanical waves and electromagnetic waves that we discussed in Physics 66, where when we covered mechanical waves, one of the important things we talked about it, that it required a medium. Every mechanical wave, a string wave, a water wave, a sound wave, they require a medium. But electromagnetic waves, they do not. They pretty much can propagate through empty space, which we call vacuum. So one of the things we're going to see in this chapter here is some of the contribution of Maxwell to electromagnetic, branch of physics. So you can think of is the father of electromagnetism, just like the Newton is a father of mechanics. Maxwell basically gave us what we call Maxwell's equations, which in a way we will see are not necessarily his equations, but he put everything together and he modified some of them, fixed some of them, and showed that, when put all together, they can describe every type of electromagnetic phenomenon. And he was able to see that you can have electromagnetic wave, which can propagate through empty space, vacuum, right? And he was even able to figure out the speed of the electromagnetic wave. And he made a very important discovery from that. And we're going to look at all of his, let's say, equations. We're going to see that those equations are, equations that we already seen before. And we will see that, let's say, some of the important things that he did was to fix some equations that, worked in some cases, but didn't in other cases. So this is one of the things that he fixed, that especially from the Ampere's law. If you remember, the Ampere's law describes how to find the magnetic field around, current carrying conductor. So we have this, you can see a conduction current, right, is carried by charged particles in a wire. So if you have a wire, and let's say, so here's your wire, and there's a current running through that wire, we said that there is a magnetic field, right, all around that wire, and you can use your right-hand rule to figure out even the direction of the magnetic field, and then use this, equation, which we called Ampere's law, right? B dot ds equals mu naught times the current. So this equation works perfectly whenever you have, let's say, current carrying conductor, any type of wire. But then there are some cases where this equation didn't work, and that's exactly what we're gonna see. So again, kind of summarize this, right? So the magnetic field associated with the current can be calculated using Ampere's law. This is the equation that we looked at, and this is a line integral on the left side that tells you that if you choose some kind of Ampere's loop around some conductor of interest, then this integral, right, b dot ds will always, or this line integral, right, will always equals to constant times the current within your loop. So that's why if there is no current, there is no magnetic field generated by that. That's why it's directly proportional to the current. Okay, so then this line integral, again, works perfectly fine whenever you have a conductor. But one of the things we can see in this slide is that if you try to apply Ampere's law in a situation where you have a capacitor, so let's say this is your capacitor, right? So you have two plates, right? Positively charged Q, negatively charged Q naught, or negative Q, and there's a current, moving thing like this. So this guy here is connected to some kind of battery, right? And the idea here is that you have a current coming from the battery. It comes and, let's say, reaches the positive plate. And if I try to find the magnetic field due to this, let's say, particular, conducting wire, I can easily do that using, let's say, this loop over here, okay? So let's say this S1, which is basically the, the surface one. I can use Ampere's law where, B dot ds around that loop will be equal to the mu naught times the current. And there is a current, so I can easily find that there is a magnetic field generated by that. But also, maybe I want to know what is the, let's say magnetic field here, somewhere between the plates. Is there a magnetic field? Is there a current over there? Because we know that there's a current that comes all the way to the positive plate, and there's a current, from the positive plate. But what happens, in the region between the plates? So that was technically a mystery for all the, physicists at the time. They couldn't understand what's going on over there. So this is where, Maxwell used the equations of the Ampere's law to, or modified, you can say that, modified equations, where he added, very important thing to have this system work. Okay, so we're going to consider, right, a system where you have capacitor and you're charging the capacitor, and you can take two surfaces, S1 and other one like this, S2, as long as it's a closed surface. So if I try to use Ampere's law to the surface 1, works perfectly fine. I try to use Ampere's law to the surface 2, it breaks down. Okay. So, and one thing he, added to this, Ampere's law, the fact that whenever there is a process where you're charging the capacitor, remember there's a accumulation of charges, right? So this one starts accumulating positive, the other one starts accumulating negative. And then one of the things we know here is that, there's going to be an electric field between them, but there is no actual current. So no conduction current exists between those plates. Okay. No charge. Remember, current is flow of charges, right? And there is no flow of charges. Charges are not moving in that region. Okay. Now, that means there's a conventional current, which is the flow of charges. And in the region between the plates, we don't have it. Okay. Again, so like what we do here, we choose those two surfaces, S1 and S2, and Ampere's law will tell us that the line integral, for the surface 1, right, is just mu naught times I. That's perfectly fine. And we can use this equation, right, apply that, but whatever I have between, for the surface 2, it will, basically not work. Okay. So therefore, a contradictory situation arises because of the discontinuity of the current. All right, so what Maxwell did basically, he solved this problem by postulating an additional term on the right side called displacement current. That means, on the right side of the Ampere's law. Remember, what we have here is on the right side, you had, so let's say this equation, right? Okay, so what he added over there is that there's also another type of current that he called a displacement current. Okay, that means it becomes sort of like mu naught times this displacement current. Okay, and displacement current is due to the fact that if you're considering plates, positive and negative, there is going to be an electric field between those plates, and the electric field, right, is increases with time. It's not, let's say, instantaneously to its maximum value. As the charges start accumulating, electric field increases because electric field is proportional to Q. Not necessarily flow of charges, right? But how much Q you have on those plates. As you start charging the capacitor, you have more and more as a function of time. So the electric field is, increasing as a function of time. And this displacement current is basically taking kind of like the area of those, let's say taking that area, right? It represents the change in electric fields moving through that area and increasing as a function of time. Remembering that we covered this electric flux, which was integral of E dot dA, which means the electric flux is just represent number of electric field lines through some area. So if you are, keeping the area constant but changing the electric field, that means you are changing the flux, electric flux. And what we can say here is this displacement current, you can see, right, is change in electric flux due to the fact that there is a change in electric field. All right, so then this is a proportionality constant. If you remember, this was the electric constant, right? Permittivity of free space. And what we get here is this displacement current is due to the fact that there is changing electric field between the plates. Okay, so this displacement current, right, has the word displacement is a little bit misnomer because this has nothing to do with the displacement, which is changing position that we talked about in chapter 2. So this is kind of like the name that got stuck, but you just think of like this. This displacement current represents the current between the capacitive plates when the capacitor charges or let's say discharges. So that's why in a way, so when you're considering that this is some kind of battery, right? There is a continual, right? Continuous, current. So that's why current comes in. Well, this is a conventional current. And then between the plates, there is displacement current. And then after that, again, conventional current. That means there is no, actual gap in your circuit. Okay, it's just you have two types of current, let's say a conventional current everywhere in the conducting wires and a displacement current, between the plates. Okay, so that's why what we have here is the contribution to the Maxwell, to the Ampere's law was that he pretty much fixed that equation, right? So the changing electric field may be considered as equivalent to a current. So that's why, what we're saying here is, as the electric field is changing, so is electric flux. So this represents changing electric field basically. So that's why, but it's easier to talk about in terms of electric flux. And what we have here is proportional to this displacement current. Okay, so that's why what we can say here is, let's say then between the plates, right, there is a current, but this is not your conventional flow of charge current, but change in electric field, current, and they're kind of equivalent. So between the plates of the capacitor, and you can think of like this is the only one of the only times you would have a displacement current. So this current can be considered as continuation of the conduction current in a wire, and this term is added to the term of the Ampere's law. Okay. So now this is known as Ampere-Maxwell law, and then you have the left side, which is just integral of B dot ds. On the right side, then you have conventional current or conduction current plus displacement current. Okay, so this is equation for the conduction current, right? So contribution to that, and this part is basically represents due to the fact that there is a changing, electric flux. Okay, that means with this, addition, right, you then can cover any type of case when there is a conduction current or when there is, a gap, but there's a change in electric field, between those, let's say, plates. And also magnetic field. So let's say if here's a conduction wire, there's a magnetic field generated. If these are the plates, so technically there's also a magnetic field generated there, but due to the change in electric field, and you get exactly same magnetic field strength. Interestingly enough, there is no difference. Magnetic fields are produced by both conduction current and changing electric fields. In a way, this was the point of this last few chapters, right? To see where you can have a magnetic field generated by the electricity. And this is a good example of that. Whenever you have a change in electric field, it generates magnetic field. That means, but the key here is changing electricity, like changing electric fields would generate magnetic field. If you have just a constant electric field, there is no magnetic field because you can see, right? This is kind of like represents that there's a magnetic field generated. And it is due to the fact that there's a changing electric field. So that's kind of like the important thing about that, because let's say, for example, if you have, so you have this, V dot ds and equals to mu naught times I plus mu naught epsilon naught, and this is changing electric flux as a function of time. See, let's say if you have a circuit like this, and this is some kind of resistive load. So what you have here is this term basically goes to zero because there is no, let's say, capacitor in the system. There is no part in your system where the electric field kind of, changes slowly like that. There's an electric field in the circuit, right? Remember, but this electric field more or less instantaneous, and that drives the current, but that drives the conventional current. But you can also have some kind of electric field without a circuit like that kind of varies with time, okay? And that can also generate magnetic field, okay? That means, for example, then what you can have here is, let's say in vacuum, when you don't have a conductor, this goes to zero, but then you can still generate magnetic field due to the fact that there is some kind of change in electric field in that region. And remember, technically the electricity or electric field can, go all the way to infinity, right? Those are, the electric field, remember 1/r square, and, it can expand all the way to pretty much infinity. All right, so let's see what we have over there. So the displacement current as the source of magnetic field on the surface boundary. And the displacement current has its physical origin in a time-varying electric field. Again, so hopefully it's all clear now. And that's the central point of the formalism of the magnetic field, which is produced both by conduction current and by the time-varying electric fields. All right, so let's look at an example here. So your 0.1 amp current is charging a capacitor that has square plates, 5 centimeters on each side. The plate separation is 4 millimeters. What we want to do here is find the time rate of change of electric flux between the plates. Right, so let's look at them part A. So a time rate of change of electric flux. That means change in flux, electric flux over time. So technically this is what we want to find. All right, so what we have here is, so let's say, remember this equation is technically, let's say if you consider the flux itself, let's say electric flux, remember this is E dot dA, right, E dot dA. And what we can do here is, let's say, remember that E for the capacitor was charge per surface area over epsilon naught, where this guy here is then Q over 8, remember that's charge per surface area, right, times epsilon naught. So this is the equation for the electric field for the capacitive plates. So let's say this is, between the capacitive plates, right? So you can see, right, that's why electric field is proportional to Q. And then so what we can do here is then this electric field represented like this, Q over epsilon naught A. And then what we have here is the A part. So let's say if you integrate that, right? So assuming that, area doesn't change, right? So it's basically A. And then cosine of 0 degree because, the electric field is parallel to the plate of the capacitor. Right. That means this flux, and I'm just being here is, you can see, right, area cancels out. So just Q, sorry, A cancels out, Q over epsilon naught. That's basically my electric field. Electric flux. Then if I'm looking at this guy here, changing electric flux over time, okay, remember now this is, you can think of like at some instant, but now it's changing. That means it's changing due to the fact that Q is changing with time, dt over epsilon naught, okay. If you remember, dq dt is the current over epsilon naught. That means change in electric flux as a function of time is equal to the current over epsilon naught. So we take this 0.100 amps because we're given our current, then divided by this constant here, 8.85 times 10 to the negative 12 coulomb square over newtons times meter square. And we calculate this as 11.3 times 10 to the 9 volts times meters per second. That's the units for the electric flux. So, all right, so that means, or changing electric flux. So that, that is for part A, which is the rate of change of electric flux between the plates. And part B here is the displacement current between the plates. Well, we know then displacement current is then epsilon naught times changing electric flux over time, okay? So epsilon naught changing electric flux over time. And this is equals to 8.85 times 10 to the negative 12 Coulomb square newtons over newtons times meter square, and times 11.3 times 10 to the 9 volt times meters per second. And what I get from here is 0.100 amps. All right. That means you can see, right, this was the conventional conduction current. And when I calculated the displacement current, I get the same answer. And it should be the same answer because current should not be different. They are kind of, we assume, to be identical, right? They're different, but they represent same continuous current. Another way you can look at it this in terms of this. So displacement current, epsilon naught over changing flux over dt, right? And remember, we talked about that this guy is nothing but current over epsilon naught. So epsilon naught, so conventional current over epsilon naught, you can see those cancel out, and you can see displacement current is equivalent to conventional current, all right? From different sources, but they are equivalent to one another. All right, so again, some historical, information regarding the Maxwell. So in 1865, he provided mathematical theory that showed a close relationship between all electric and magnetic phenomena. Okay. So he has 4 equations, and the important thing, again, not only that he put together all of those equations and fixed some of them that were, let's say, not complete, he also predicted the existence of electromagnetic waves and that it can propagate through, through empty space, through vacuum. And one of the interesting things that Einstein showed that these equations are in agreement with the special theory of relativity. Interestingly enough, Albert Einstein basically took, the Maxwell's equation to be the reference, right? So basically the basis for his theory of relativity. Unfortunately, we won't be able to probably get to theory of relativity, but if we would, let's say we will consider that one of the things he does in his theory of relativity, he takes the electromagnetic wave speed to be constant everywhere in the universe. And the entire then theory of relativity is basically based on that fact. That means speed of light, which we'll see the electromagnetic wave is a speed, is light, right? That means as electromagnetic wave is moving in empty space, for every observer in the universe, regardless of their relative motion, they will always measure the same, speed for this electromagnetic waves. All right, so these are Maxwell's equations. So here's the first one. Integral of E dot dA equals Q over epsilon naught. Well, we have seen this before, right? This is, Gauss's law, which tells you that, electric flux, right? E dot dA equals charges enclosed or inside, that Gaussian surface over epsilon naught. Okay, so that's something we have seen before. But, just like, Isaac Newton, when he, let's say, wrote down his laws of motion, most of those equations, were not discovered by him, but he was able to put everything together and make it sort of like the physics law. Same thing is here. So first equation is basically Gauss's law. Gauss's law for the, electric flux, and, in terms of where do you get, electricity, and it depends on some kind of, source charge. Second one is also Gauss's law, but for the magnetism, it's B dot dA. And it's equals to 0. And it has to be equals to 0 because this pretty much represents the fact that if you're considering, let's say magnet, north, south, any type of surface that you try to enclose it, you're never going to find flux, for that surface. So whatever comes out over here goes and comes in the other side, okay? That means one of the things we have here is This is due to the fact that there is no such thing as magnetic monopole, okay? That means if I consider any surface and have tried to find the flux for that surface due to the magnetic source, I'm gonna get zero, because of the fact that you can never have a single north or a single south pole. And every time, whenever they come in pair, so you can see, right, on the right side, you're always gonna get zero because your net magnetic, let's say source is always north plus south together gives you zero. Okay, that means net magnetic flux to the closed surface is zero. And again, this is due to the fact that there is no such thing, at least we haven't discovered yet, there's no magnetic monopole. Here's the third equation. And again, this is something we have seen before, and that's the Faraday's law. So Faraday's law tells you that you can generate electricity, right? So it says it's a generate electricity from magnetic source as long as you're varying the strength of the magnetic flux. That means this is Faraday's law of induction. And we covered that in chapter 23, where changing a magnetic flux, well, gives you an, induced current. Now remember, induced current means that there was an electric field, in the first place to get that current. So a third law for the, Maxwell's equation is basically Faraday's law, which describes the creation of electric field by changing magnetic flux. And remember, we can say that there's an induced EMF, induced current, right? And we consider this, in chapter 23. All right, so one last equation is Ampere's law, which then was modified, right? So it's Ampere's Maxwell law. So describes the creation of magnetic field by changing electric field and by electric current. That means equations 3 and describes that you create electric fields by varying magnetic fields. Here, you create magnetic fields by varying, let's say, electric fields, right? So that's kind of like the important thing. That means there's a relationship how you can, generate magnetic and electric fields from another one, right? The line integral of the magnetic field around any closed path is the sum of mu naught multiplied by the net current through the path and epsilon naught mu naught multiplied by the rate of change of electric flux through any surface bounded by that path. Okay, so those are, Maxwell's equations. But to describe the entire electromagnetic phenomena and electromagnetic waves, we also have to look at one more equation. And this one is that, you can say once the electric and magnetic fields are known at some point in space, remember, if you have an electric field, well, they're bound to be electric force. If you have a magnetic field, they're bound to be a magnetic force. And then the net force is then vector sum of electric and magnetic forces, right? And this is then electric force, test charge times the electric field. And this is then the magnetic force, which is Q V cross B, okay? That means you have now kind of complete electromagnetic, let's say, force, right? So that's why this is not electric or magnetic. This is, I guess, electromagnetic force, which is due to the, let's say, presence of electric field and the presence of magnetic field. Any charged particle then can have those two forces acting on them. So this is known as a Lorenz's force. Okay, so that means this is relationship, right, that describes the complete, electromagnetic force on a charged object. Again, you have to understand that this works only for a charged object. This will not work for a, let's say, neutral object, because the requirement here is there's a charged test particle. So then Maxwell equations, together with this force law, you can see, right, completely describe all classical electromagnetic interaction in vacuum, okay? I mean, it describes everywhere, right? But also in vacuum. Because one of the things we can do here is, if we go back to look at those equations, 4 equations for Maxwell, we can see that if you're considering empty space where there are no source charges, so let's say you take this equation, right? If Q is 0, then this is equals to 0, right? And if I is 0, then B dot dA here is 0. Okay. And shows that electromagnetic waves move at the speed of, and this is kind of like what, one of the things he did, right? To complete that and show that, electromagnetic wave can actually move in, empty space. And that's due to the fact that there's also equation 3, right, which is E dot ds equals negative change in electric. Well, there is mu naught, then change in electric flux over time, right? There's also epsilon naught. And then this equation, E dot ds equals negative change in magnetic flux over time. That means even in a case where there are no charges, right, in empty space, you can still generate magnetic field or electric field if you have time varying electric field or time varying magnetic field. And he predicted that in that case, the electromagnetic wave can still propagate in empty space. And when it does, it will move then with the speed, which, we will see a little bit later on, right? But when you calculate velocity of electromagnetic wave, it is nothing but 3 × 8 meters per second. Okay, so then he predicted that light, or electromagnetic wave is nothing but, light, or light is, electromagnetic phenomena or electromagnetic radiation. So by radiation means some, a way that kind of radiates from some kind of distance source. All right, so let's look at an example here. Let's assume an electron moves through a uniform electric field, and you're given the electric field, which is 2.5 I hat plus 5 J hat volts per meter, and uniform magnetic field, which is B equals 0.4 K hat Tesla. Determine the acceleration of the electron when it has a velocity V equals 10 I hat meter per second. So this is an example of where we can see that to solve this problem, where we have some kind of an electron, right, charged particle, moving in an area where there's an electric field and magnetic field. So technically what we have here is, so there's a magnetic field out of the page, like this, right? And there's an electric field I hat plus J hat. So I guess, let's say an electric field somewhere like that. So this is B field, and then this is E field, right? So let's say if you have a charged particle that is moving in a horizontal direction. So let's say here's an electron moving with this velocity. So there's going to be a force. Well, but there's going to be force that is both electric and magnetic, because, well, there's electric field, there's electric force. And electric force, remember, is always in the direction of electric field. So if I kind of do this, so there's going to be electric, oh, sorry, that's an electron. So electric force will be in opposite direction. So this will be electric field, electric force. And there's a magnetic force. And magnetic force will be, if you take your right hand or left hand, right, fingers in the direction of the velocity, curl in the direction of magnetic field, and find the force on electron, you will see that magnetic force will be in this direction. All right, there's going to be a force acting in that direction, and then we can basically see, let's say, in terms of in which direction will be the acceleration. Okay. All right, so remember, this is technically equals mass times acceleration as a vector, right? And then here we have Q times E plus Q times, or, in this case, this Q going to be E, but let's say that's general equation, right? So here V cross B equals mass times acceleration, right? So then if I'm solving for acceleration, then this is going to be in terms of E, factor out, right? And then you get E plus V cross B and divided by the mass. Okay. So that means we need to, let's say if this is a vector, right? So we need to, first find, first find the cross product, and then we have the electric field, and just add them as, as vectors. So let's do this V cross B. Okay. So remember, one of the things we can do here is this as a determinant, right? So I have I hat, J hat, and K hat. So let's say if I'm looking at the velocity, velocity is 10, 0, 0. Magnetic field is 0, 0, 0.4. And from here, if I do that, remember, so this is, going to be for I hat minus J hat plus K hat, right? So if I kind of look at I hat, so kind of maybe do it like this, I can see I get 0, 0, 0, 0.4. Here, if I'm doing then a J hat, so then I have 10, 0, 0, 0.4. And if I'm doing K hat, then I take this. So this is then 10, 0, 0, 0, K hat. And then from here, I can see that this is going to be 0, because when I do the cross, like this 2 by 2 determinant, I'm going to get 0. This is also going to give me 0, because if I do 10 times 0 minus 0 times 0, I'm going to get that. So, but this one will survive, because what I have here is negative. So I'm going to give me 10 times 0.4, which basically give me 4, minus 0 times 0, 0. Nothing but, let's do it here, negative 4. That means this cross product is, 4 times J hat. All right, so then what I can do here is then I have E or let's say E over M, right? So then here is electric, which is 2. All right, so let me do it here so I have more room. So electric field over M. So then I have 2.5 I hat plus 5 J hat, then plus, and that's then the V cross B. And this is just then negative 4 J hat. Okay. That means you can see, right, those two together, there's those two, I can combine those two together, right? So I'm going to get just, 1 J hat. So 2.5 I hat plus 1 J hat. And then you have the electron. You can just put the charge of the electron divided by mass of the electron times that. Then we can get acceleration. If I plug everything together afterwards, is then negative 4.39 I hat minus 1.76 J hat, and this whole times 10 to the 11 meters per second squared. And that's my acceleration. Again, the same solution you can find on the lecture notes, but this is kind of like the idea. That means you have to take each term, right? Find the V cross B, and then add electric field and V cross B, right? And just add them as vectors. That means you can combine J hats or I hats together, right? But you cannot combine I hat with a J hat. All right, so then, and we can calculate the acceleration from that. All right, so this is basically to show that what Maxwell did, right, when he was trying to look at the speed of electromagnetic wave in vacuum. So he figured out that electromagnetic wave consists of two fields, electric field and a magnetic field, okay? And they are actually changing with time. So there are time varying fields. And when they, let's say here's you have electric field, let's say here you have magnetic field that are perpendicular to one another. And one of the things we can do here is if they are changing, so you get like a, E cross B, if they're changing with time, then their cross product, if you use right-hand rule, right, your fingers in the direction of E, then curl in the direction of the B, one of the things you will see is that this basically requires this field to move with some velocity, perpendicular to both of those fields. And that velocity, after he calculated, ended up just being equals to 1 divided by square root of mu naught times epsilon naught. That means just depends on those constant. That means it's a constant. It doesn't depend on anything else. And when he calculated this, he got then 3 times 8 meter per second, 3 times 10 to the 8 meter per second. That means electromagnetic wave is moving at same speed as the light moving in vacuum. And they already knew how fast the light was moving in vacuum, even though they didn't understand what light was. But here, he was independently, he didn't know that electromagnetic wave is a light, but he was able to find the speed of electromagnetic wave in vacuum. And the only way you can describe this, right, how close they are, or how identical they are, if you take the light to be basically same as electromagnetic wave. That means light is another form of electromagnetic wave. And it is produced by a changing electric field, which induces magnetic field, and changing magnetic field, which then induces an electric field. That means that's why you don't need any medium to propagate. All you need is electric and magnetic fields that are varying with time. Okay, so this is, again, complete picture of that. So you have electric field and you have magnetic field. And as they are, let's say you have on the y-axis electric field, on the, z-axis the magnetic field, you can see, right? Because of the way they are changing, right? This, cross product, E cross B, then gives you this vector C, which is the speed of light. And that means it is moving perpendicular to the direction of that oscillations. All right, so the direction of propagation in the positive x direction, the y is parallel to the electric field in a y direction, and the magnetic field is in a z direction. And that's kind of a requirement. They always, perpendicular to one another, okay? So waves in which the electric and magnetic fields are restricted to being parallel to a certain direction are said to be linearly polarized waves. Okay. And one of the things we're going to do here is to define a ray, which are going to be used a lot, especially starting from chapter 25. So ray is basically as the line along which wave travels. All rays for these waves are parallel. That means we can then take the direction of the propagation and represent this in terms of just a ray. That means just like an arrow, right? Rather than represent this entire propagation with, time varying electric and magnetic fields, which we can still do that, but a ray is much more simplified picture of that. Okay, so this whole collection of waves is often called plane wave, and the surface connecting points of equal phase on all waves, which we call wavefront. And it's a geometric plane. In a way, we have seen this before, if you remember. So let's say if there's a source, see, like, let's say wave is propagating like this. So those lines are wavefronts, okay? And they are basically, you can think of those are crests, right? So it's kind of like wave goes like this. All right, so I'll try to do my best, right? So it's kind of like this. That means the crests are, can be represented like that. And what you get here is those crests represents the, in which direction, right, the wave is propagating. So we call it wave fronts. So this ray would be, if I take that and represent all that propagation with an arrow, with a ray, right? So let's say I can say it's moving in this direction. It's a perfect, simplified picture of that, okay? So I can represent this with that ray. All right. So in comparison, a point source of radiation, right, sends a wave out in all directions. So that means, I can say that it's kind of moving in this direction, in this direction, in this direction, representing all those waves that can, originate from that source, because it's a plane, right? You can even think like it's in all three dimensions. It's kind of like moving. So a surface connecting points of equal phase for this situation is a sphere. So we call this the radiation from a point source spherical. And again, spherical because, for example, if there's a speaker, right, you can hear the sound wave in front of the speaker, behind the speaker, sides of the speaker, on top of the speaker, below the speaker, right? Because it, propagates or radiates, right, in all direction. So that's why it's kind of like it's propagating as a sphere. Okay, so obviously it's a wave, and it's a wave that's traveling. So that means we have to go back and remember the equation for the traveling wave. Okay, so and that equation is always, so this E is as a, E as a function of what we can say, like probably the better will be E as a function of position and time as it's propagating along the x-axis, right? It equals to the E max, which is its amplitude, and times cosine of kx minus omega t. So remember, so I can rewrite this also in terms of E max, then cosine 2 pi over the wavelength times x minus 2 pi over the period times t. That means this is, equation where we can see that those k and omega in this equation represent the wave number. See the angular wave number, right? K here is 2 pi over the wavelength. So this lambda is the wavelength of that wave. And then here this omega is 2 pi f, or, technically 2 pi over the period. We can also do it in terms of that. So then the speed is the wavelength times frequency, or wavelength over the period, since frequency is 1 over the period, or I can represent it in terms of the wave number and angular frequency, that's omega over k. So you can see, right, all those three equations will give me the speed of light or speed of electromagnetic wave in vacuum. And when Maxwell put all those values together, he was able to calculate that speed to be 3 times 10 to the 8 meter per second. And, once you have that, remember it's constant, then you can use that to figure out the wavelength of the electromagnetic waves. And one of the things he was able to see is that the electromagnetic wave has, very big, let's say range, where we can have a wavelength that can be as small as, picometers and as large as, let's say, hundreds or thousands of meters. So we're going to talk about it in a little bit, but, this is a nice picture of how the electric fields, which vary with time, like a sinusoidal like this, and exactly same way magnetic fields. That means they are, reinforcing each other. So if, as this one is positive, the other one positive, and then electric field becomes negative, the other one becomes negative, and you can see, right, as they change, the other one is changing. That means changing this induces that, and changing that induces this. So they basically completely induce one another and propagate in perpendicular to their direction, in vacuum. They do not require any medium. They generate this wave by just inducing magnetic and electric field on one another. All right, so this is kind of like the mathematics of this. You don't really have to kind of worry about this. But remember, this is electric and magnetic fields that we just talked about, right? Time varying equations for that. The idea here is if you find, the derivative of that, right? Which is dE dx, and let's say dV dt, right? Is just to, you can see that, at the end, you can simplify this to just be in terms of the amplitudes. So electric field amplitude over the magnetic field amplitude is equals to the speed of light in vacuum. Same way as we talked about, right? Omega over k, because we basically end up with this equation. Because remember, so if I end up with just that, then I can see that what I get here is omega over k, right? Omega over k is equals to E max over B max. But we know that omega over k in the previous slide is just, speed of light. That means E max over B max is also equals to the speed of light. And that's basically what we have. That means anytime you take electric field divided by the magnetic field, even if time varying, right, you will get the speed of light. But the easiest way maybe for you to get that to divide the amplitudes, electric field amplitude over the magnetic field amplitude. Okay, you can see right at every instant, the ratio of the magnitude of the electric field to the magnetic field, right, E in an electromagnetic wave equals to the speed of light. Okay. So let's solve a few examples here. So electromagnetic wave in vacuum has an electric field amplitude of 220 volts per meter. Calculate the amplitude of the corresponding magnetic field. All right, so, well, it's easy enough now because let's say, remember, the electric field, it's in vacuum. That means it will generate magnetic field. And this is, let's say, at some instant, right, when its value is 220 volts per meter. But remember, the whole time, the speed of this wave, right, will be, speed of light. That means we can always say that, this E over B here is equals to C, and just use that to calculate then magnetic field. That means you can say that magnetic field will be in terms of E over C, right? Plug in that and calculate then the magnetic field. In this case, 733 nanotesla. Here's one more equation, an example. So you have in SI units, the electromagnetic field in an electromagnetic wave is described by this equation. So we have the equation, or the electric field, as a function of time at that instant. So it's given as EY equals 100 sine 1 times 10 to the 7 x minus omega t. So we're given, the electric field of the electromagnetic wave. All right. So let's see what we can do with this. Okay. So one of the things we can, let's say use this equation is to pick up some of the things inside the equation. Okay. So for example, this 100 over here is then maximum electric field amplitude. That's an amplitude, 100 volts per meter. Also, this guy over here in front of X is then the wave number. That's our K. So K here is 1 times 10 to the 7, and it has a units of radians per meters. Okay. Because, let's say when it says, find the amplitude of corresponding magnetic field oscillation, well, I can find always one of the amplitudes as long as I have the other one, because C is equals to E max over B max. And I do have an E max, so I can again solve for B max, which will be then E max over the speed of light. All right, so then 100 volts per meter divided by 3 times 10 to the 8 meter per second. Calculate them together, 0.333 micro Tesla. That's part A. Part B, it says find the wavelength, lambda. Well, wavelength is just, related to the wave number, remember, right? So remember, K here is equals to 2 pi over the wavelength. That means wavelength is equals to 2 pi over the wave number. So we can use that. 2 pi divided by 1 times 10 to the 7 radians per meters. You can remember, right? This is 2 pi radians, so radians cancel out. So you get a meters as a unit. We're going to get 0.628 micrometer. That's our wavelength. For part C is find the frequency. All right, so I would have been able to find the frequency, let's say if I was given omega, and I just, omega, remember, equals 2 pi f. Very easy way of finding, frequency, but I'm not given omega here. But there are other ways to find, frequency, because speed of light is wavelength times frequency. We have this equation as well. Well, then I can say that frequency is speed of light over wavelength. So 3 times 10 to the 8 meters per second over 0.628 times 10 to the negative 6 meters. Plug in, calculate, and we get 4.77 times 10 to the 14 hertz. And that's basically the frequency of this wave. All right, so we were able to basically put it together, and that's kind of what I want you guys to get out of this type of equations, to understand how you can pick up some of those things. All right, so now electromagnetic wave, just like any other waves, right? Well, they carry energy, and we want to find, let's say, how much energy is associated with this, certain type of wave. And one of the things we can do here is then we can calculate the rate of flow of energy in an electromagnetic wave. And, mathematically speaking, then if you try to do that, what you can calculate here is what we call a pointing vector. Okay, so this S, vector S is called pointing vector, and is a cross product of electric and magnetic fields. You can see, right? So 1 over mu naught is just a constant. So that means, remember, the cross product always gives you a vector. And when you do E cross B divided by that by mu naught, then that gives you the pointing vector. Okay. That means this just gives you the rate of flow of energy. That means, energy per time, right? So that means, you're going to get some kind of amount of energy as a function of time. And let's say here's the direction of that pointing vector. It will be, again, remember, if you do a cross product, right, E cross B, you can see, right, this pointing vector is in the same direction as the speed of light, because the cross product is, always going to give you, if you do the cross product, in a positive x direction. So if you do the right-hand rule, you will see that your thumb is pointing in a positive x direction. All right, so its direction is the direction of propagation. That's for the pointing vector. So this is time dependent, because electric field is time dependent, magnetic field is time dependent, so is pointing vector. So its magnitude reaches a maximum at the same instant as the fields. So this is the power per unit area. So that's kind of what we have for this pointing vector. It's power per unit area. So in a way is power per unit area, right? That means it's watts per, well, the watt is the units for power, meter square is the units for that, the area. Okay, so watts per meter square, or watt, remember, is the units for joules per second, so it becomes joules per second times meter square. So the magnitude of the vector represents the rate at which energy flows through a unit surface area perpendicular to the direction of the wave propagation. That means, in a way, what you get here is how much energy going through some area as a function of time. That means, let's say if I choose some kind of area A, and then as this wave is moving to that area, then I can say, okay, how much energy goes through that area, as a function of time. So that's why, joules per second per meter square. Okay, you kind of get two information, let's say area of interest and how much energy flowing through that as a function of time. Okay. Now the magnitude, remember, so technically you have, this is the vector, so which is E cross B over mu naught. But remember, if E and B are perpendicular to one another, remember, you can write this as EB sine of theta, but if they're perpendicular, sine of theta is just 1. So that just becomes EB, and then divided by mu naught. And that gives you just the magnitude. So that's why you can have S is equals to EB times mu naught. That's just the magnitude of the vector. How do you find the direction of this vector? Remember, it's always in the direction of the wave propagation. That means same direction as the speed of light. So now, one thing we can do here is from this equation, I can rearrange it, because remember, C is equals to E over B. I can rearrange it where I can substitute E, and just, because you can see, right, E is equals to then C times B. So then if I substitute for E, I get B squared times C over mu naught. And that's this guy over here. Or I can see that B is equals to E over C. And then now if I substitute for B, then I get E squared over mu naught and times C. That means you can calculate, the magnitude if you just have one of the vectors. Right. So another thing we can calculate is the intensity, which, remember, since the Poynting vector, so like it varies with time, right? We can find maybe like the average Poynting vector value. And once you find the average, then that average is then defined as the intensity. Okay, so intensity is nothing but the average Poynting, vector value. And you have then E max, B max over 2 mu naught. So the base, this 2 here is addition to that in order to basically make this as an average value. And again, those two equations are just, substituting, for the E or B and just writing in terms of only one, let's say only one variable. So this is just in terms of electric field. This is just in terms of magnetic field. All right, so let's look at an example here. So in a region of free space, the electric field at an instant of time is 80 I hat plus 32 J hat minus 64 K hat. So it's like three-dimensional electric field. And the magnetic field is 0.2 I hat plus 0.08 J hat plus 0.29 K hat microtesla. Again, that means you have kind of like two three-dimensional vectors. Show that the two fields are perpendicular to each other. All right, to determine the Poynting vector for these fields. All right, so there are two ways, we can determine or show that two vectors are perpendicular to one another. So, and the best way to do that, let's say, is to show that dot product. Remember, if you're doing dot product, right? So if you do the dot product, what you will get is EB sine of theta, but you will get 0 if theta happen to be 90 degrees. That means one of the things you can do here is take the electric field, take the magnetic field, and do the dot product. And if you get 0, that means they are perpendicular to one another. So that's basically by far the easiest way of showing that. And that's what we're going to do. So we're going to take electric field, which is 80 I hat plus 32 J hat minus 64 K hat, and do the dot product with the magnetic field, 0.2 I hat plus 0.08 J hat plus 0.29 K hat. Okay. So remember the dot product, if you recall, the dot product between two vectors is end up being just Ix Bx plus Ax Bx plus Ay By, and let's say plus Az Bz. That means you are doing the product of the components, because when I do this 80 times 0.2 and then do I hat dot I hat, this is equals to 1. But when I do I hat dot J hat, let's say if I do this term times that term, I'm going to get 0 because I hat dot J hat is 0, or I hat dot K hat is 0. That means I can ignore those and only do in terms of this equation over there, which we learned in previous chapters. That means I can just say it's Ax, or Ex times Bx plus Ey, which is 32, times By, which is 0.08, plus Ez, which is 64, times Bz, which is 0.29. Okay. Adding those all together will give us 0. That means you can see that if we doing the dot product of a vector and you get basically a 0, those vectors are perpendicular to one another. By far the easiest way of finding that. All right, so that's part A. Part B, it says then determine the Poynting vector for this, for these fields. Okay. Now that's a little bit harder job, right? So let's We need more room for that. So S is equals to E cross B over mu naught. All right. So that means what we're gonna need to do right now is find E cross B. Okay. So there are several ways we can do that, right? So there are several ways we can do that. And let's say you can do just directly E cross B and use the, I hat, J hat, K hat. So put, let's say, those vectors and let's say calculate that. But there's also another way I can do this. So that means, so right now, let's say factor out 1 over mu naught. So let's say for now, let me just put it like that. And what I have is this. So electric field is 80 I hat plus 32 J hat minus 64 K hat. And this is cross 0.2 I hat plus 0.08 J hat plus 0.29 K hat. All right, so let me kind of give myself more room. So minus 64 K hat. So cross, so 0.2 I hat plus 0.08 J hat plus 0.29 K hat. So I have that. All right, so then this is equals to, so 1 over mu naught. So then what I do here is this. So if I take this, right, so basically multiply everything together. So I can see that I do 80 times 0.2. And I get I hat cross I hat. Then plus 80 times 0.08 I hat cross J hat plus 80 times 0.29 I hat cross K hat. Then plus, and you go to the next one, 32 times 0.2 J hat cross I hat plus 32 times 0.08 J hat cross J hat plus 32 times 0.29 J hat cross K hat. Then minus 64 times 0.2 K hat cross J hat minus 64 times 0.08 K hat cross J hat. Sorry, this is I hat. Then minus 64 times 0.29 K hat cross K hat. So you can kind of do it like this. All right, so seems like tedious, but if you go back then you can see several things that can be simplified. See, in a cross product, I hat cross I hat is 0 because that's a cross product between parallel vectors, and cross product between parallel vectors is 0. That means here you have then J hat dot J hat. This is 0, and K hat is also 0. K hat cross K hat. That means those three are, right away become 0. All right. So then you have, other terms that technically survive, right? So then you have to kind of look at it in terms of this. So let's look at then this guy over here. So 80 times 0.08. So that gives you 6.4. And then you have I hat cross J hat. So if you do I hat cross J hat, so remember it's still 1 over the mu naught. All right, so doesn't want to write on that. Let me do it like that. So 6.4 K hat, because I hat cross J hat is K hat. Then the second term, 80 times 0.29. So that's going to give me 23.2. okay? But I hat cross k hat is actually negative j hat. So it gives me negative j hat. All right. So then the third term over there, 32 times 0.2. So that gives me negative 6.4. And if I do I hat cross j hat, that gives me k hat. Now this term over there, 32 times 0.29. All right. So that gonna gives me 9.8. I hat, so it's j hat cross k hat. Again, the way you can figure out, right? See, j hat. So you have your fingers in the direction of j hat. So not cross out of the page, which is k hat. So you will see that your thumb is pointing in a, I hat direction. That means the cross product of j hat cross k hat is positive I hat. All right, then the next one, which is this guy over there, negative 64. So negative 64 times 0.2. So that gives us 12.8. So it's negative, so negative 12.8. And then you do k hat cross I hat. Okay, so k hat cross I hat, and that gives you a j hat, positive j hat. So like that. All right. So finally down to last term. So negative 64 times 0.08. So this should give us 5.12. So negative 5.12. But then when you do k hat cross j hat, you get then negative I hat. So that cancels this one. So you get I hat like that. All right. So we get this. And then you can even simplify because 6.4 k hat, negative 6.4 k hat, those cancel out. And then what you end up here is two positive I hat terms that you can add them together, and two negative j hat terms that you can add them together. And once you find those, then divide that by the mu naught, pretty much, right? And what you will get here is basically the answer at the end, which let's say will be 11.5 I hat minus 28.6 j hat, and the units are watts per square meters. And that will be the answer for the Poynting vector, okay? Now, in which direction it is, right? So you can see that you have I hat, negative j hat, right? So technically that's, in a fourth quadrant somewhere. So technically you can then use this, inverse cosine of, or inverse tangent of, horizontal, vertical component over horizontal component to find that you basically get negative 68 degrees roughly from below positive x direction. So that's the direction of that Poynting vector. Like that. All right, so as you can see, right, so the cross product, especially three-dimensional cross product, is relatively tedious, but this is another way of basically doing that. All right. Now, the next here is we talk about electromagnetic waves. And one thing we have here is that electromagnetic waves, right, come in different, let's say, flavors, different frequencies, different wavelengths. And what we see, what we talk about, what we mean when you say light, is only a very small portion of the entire electromagnetic spectrum, okay? So, and what we're gonna talk about here is then types of, let's say, electromagnetic waves, which is the spectrum. You can see in this spectrum of electromagnetic waves. And I'm gonna kind of quickly go over them here to, in this lecture, but I have a few more, slides in the lecture notes that you guys can go over and, look at some of those, specific type of, let's say waves. But what we have here is generally this is the region for the radio waves. Right? So the radio waves are always, or you can think of like they are considered to be the longest wavelength, waves. That means they have the longest wavelengths, where the wavelength can be thousands of meters. You can see, right, this is like 1 kilometer, and you can even have a long wave. So this is still a radio wave. That means you can still have, thousands of, or 10,000 kilometers and things like that. So that's why the radio waves are used, for, let's say, radio, FM radio, AM radio, and things like that, because this signal, right, so it has such a large, wavelength, then technically they can go above the mountains or buildings and things like that, right? That means they can reach, like a really large, let's say, the area. And then you have microwaves. So microwaves, you can see, right, the wavelength is, generally in few centimeters. And it's very good for, let's say, in a microwave oven, right? So in microwave oven, you are using basically a microwave electromagnetic waves, where, you use the electromagnetic wave to heat up your food. And what it does, it basically, it sends, those, electromagnetic waves, which have like few millimeter or few centimeter wavelength. And what is electromagnetic wave? Nothing but pure energy. And that energy then is absorbed by the water in your food, right? And then it warms up, and then your food warms up, pretty much. So that's kind of like how the concept of electromagnetic wave is. And generally, you can see right there, go from few millimeters to few centimeters, right? 10, 20, 30 centimeters. And they're very good for, for example, astronomical measurements of, let's say, a dust and, a gas, right? When you're trying to find an area where there's a gas and dust, it's very, useful to look at in terms of microwave, like astronomy. But one of the things we have is that for the microwaves, right? So you need, telescope that has to be above our atmosphere, because our atmosphere allows radio waves to pass through, but it blocks some of the, or most of the microwaves. And then what we have here is the infrared. So the infrared, you can see, right, is few millimeters, right, to a micrometer. That means, what you have here is the wavelength is decreasing. You can see, right, you're going in the direction of the, so like a wavelength goes like this, right? So it increases in this direction. So you have then few millimeters to micrometer, that's infrared. And that is the electromagnetic wave that can be used, right? Or that's the electromagnetic wave that, let's say, objects around you or people are glowing at. That means, for example, when you are radiating energy, we are radiating energy at infrared. And we don't see ourselves glowing, or the objects around us glowing, because our eyes are only sensitive to this small region that we call, visible spectrum. Okay, so this visible spectrum is the only region our eyes are sensitive to, which, when we talk about that, right, that spectrum is basically, between 400 nanometers to about 700 nanometers. That's our, let's say, visible spectrum. And you can see, right, so this tiny region is right here, what we can see. And our eyes, interpret different wavelengths as different colors, pretty much. So just like our ears interpret different frequencies, different pitch. So that's why 20 hertz, 20,000 hertz, remember we talked about, right? Different frequency, different pitch. Same thing with the light. So if you have a light that has a wavelength of, let's say, 700 nanometers, our eyes interpret that as a red. Something that has, let's say, 500 nanometers, it's like yellow-green. 400 nanometers is basically a violet or blue. And, combination of all of those, right? Violet, blue, green, yellow, orange, red, that's, all the colors of electromagnetic spectrum, or the visible light. And if you put all of those together, you pretty much get white light. Okay. All right, so electromagnetic waves, you can see, right, if you kind of continue decreasing the wavelength, you get to the ultraviolet, which goes from few micrometers to few nanometers. And that's basically, obviously it has to be, below 400 nanometer. So, because 400 nanometer roughly is ultraviolet, and let's say 300 nanometer, 200 nanometer, our eyes cannot see that type of color anymore. And what we have here is that ultraviolet. After ultraviolet, then we get X-rays, and more or less we get gamma rays following that. And those are very, very small wavelengths. That means wavelengths are so small. And one of the things we have here is, you can see that as wavelengths increasing, as wavelength is decreasing, frequency of those wavelengths increasing. So that means as you go from radio waves, which has a frequency of, let's say, 1,000 hertz, to a visible light, which is, frequency generally about 10 to the 14 hertz, to a gamma rays 10 to the 22 hertz, you get much, let's say oscillation, much higher frequency. And, generally energy is then proportional to the frequency. Greater the frequency, more energy in the wave. So that's why gamma rays and X-rays, have a lot of energy associated with those waves, and it can be very dangerous for humans. You get exposed to a gamma ray for, like, let's say, extended period of time, you can actually die within days. So that's why, for example, an X-ray, only, let's say you get X-ray only when it's important, right? So let's say it has some medical benefits, but definitely you don't want to go and do that every day. Ultraviolet is also can be dangerous because the sun has kind of, let's say some ultraviolet, right? So some of the ultraviolet radiation has, let's say, especially closer to the X-ray region, right? It has a lot of, energy, and, those energy when it's, absorbed by your skin can cause the skin cancer and things like that. So yes, some of the ultraviolet is good for tanning, but too much of it, or certain type of ultraviolet can also be dangerous. Now, one of the things we have here is, which is very good for us, is that our atmosphere blocks most of, so let's say it blocks pretty much all of X-rays, gamma rays, and most of the ultraviolet. Our atmosphere, is saving us every day, because if we are exposed to the sunlight's gamma rays and X-rays, if there's no atmosphere, all the living things will die on Earth. And it also blocks most of the infrared and microwaves. That means visible and a little bit of ultraviolet and radio waves are the ones that actually can penetrate our atmosphere and go through the atmosphere. So that's why, you can do the ground telescopes, right? You can have a visible telescope, visible light, or, radio wave telescopes. But everything else is, you have to go above atmosphere to do X-ray, astronomy or microwave astronomy and things like that. All right. So, and, a visible light is something I want to, talk about more, right? So part of the spectrum detected by a human eye, and is basically has those wavelengths and frequencies, right? Generally, we talk about wavelengths when we talk about, visible light, visible spectrum. So you can see, right, every color has a specific range. So 400 to 430 is for the violet, 625 to 700 is for red, right? And so on and so forth. So that's why, for example, if you have a 800, a nanometer wave, right? We can't see that. Or same thing, if you have a 200 nanometers, we also can't see that. This is ultraviolet and this is infrared. So our eyes only, sensitive to that, range of the electromagnetic waves. All right, so let's look at, an example here. So suppose you are located 180 meters from a radio transmitter. And how many wavelengths are you from the transmitter if the station calls itself 1150 AM? Okay, so the AM band frequencies are in kilohertz. Okay, so you're given, your position, right? So that means how far away you are. And obviously you want to know what is the wavelength of the, let's say, of this particular wave. And then you can, assume that this is still a light. That means it is moving with the same speed as, technically speed of light in vacuum and speed of light in air are, you can think like are identical. We have very little decrease in, light speed in air compared to vacuum. So one thing we can do here is then find the wavelength, speed of light in air, right? Same as in vacuum, divided by the frequency. That means we take, 1150 AM as in terms of 1,150 times 10 to the 3, hertz, right? Or per second. So we get 261 meter for the wavelength. That means if you are 180 meter apart, away from that, let's say, radio transmitter, then you're not even one wavelength away from it. You're only about, 77.2 6.9 wavelengths away from that transmitter. Part B here, it says, what if the station is 98.1 FM? Well, FM is in megahertz. So they do the same calculation where you take speed of light divided by the frequency, but this is now in terms of the, let's say, 98.1 times 10 to the 6 hertz, and you get 3.06 meters. You can see what a big difference it is, right? So that means when you stand 180 meters away from it, you have almost 60 wavelengths, right? Basically, in terms of there 60 wavelengths before, let's say the light gets to you. So that's why AM is better, because it has much higher, wavelength. So it can go around, buildings and things like that. And you can have an AM, in your car, right? Even if you're outside of the city. Or FM, right? It has a very small wavelength, right? So then let's say the mountains or buildings, right, can actually block the FM. So that's why sometimes your radio kind of loses the signal because of the, let's say higher bandwidth, right? Higher frequency. But also the good thing about this is that, the smaller the wavelength, higher the frequency. That means it's more energy. That means it's